Hello, welcome back, wherever you are tonight. And I do wonder, genuinely, at this hour, what particular shape of quiet has gathered around you? What kind of room? What kind of light? What small, familiar sound nearby tells you exactly where you are without needing to open your eyes? I'm glad you're here. This is a good hour to have arrived at. Whatever the day asked of you, it's behind you now. Go ahead and settle in properly. Not the tentative kind, still half listening for one more thing to happen. The complete kind. Let your weight sink entirely into whatever is holding you up. Let your shoulders finally set down whatever they've been carrying since this morning. Let your breathing slow into its own rhythm, the one that doesn't need managing, just allowing. You don't need to hold on to anything tonight. What stays with you will stay because it found something in you already waiting for it. The rest will simply pass through, gently, and that's exactly as it should be. This isn't a lesson. It's a long, slow unfolding of something true, offered at whatever pace lets your eyes close on their own. If you're new here, welcome. This is Late Space, and what we do is take the largest ideas we can find and slow them down until they fit the shape of a quiet evening. If this feels like somewhere you'd like to return to, a gentle like or subscribe helps other people find their way here too, on their own restless nights. But that's for later, for the more awake hours. Right now, there's only this. Tonight, I want to ask you a question that sounds, at first, almost simple enough to answer in a single sentence. And I want you to notice, as we spend the next while together slowly working through it, exactly how much that simple question actually contains. How many layers of physics, engineering, patience, and genuine human ambition are folded quietly inside it, waiting to be unpacked? How long would it take us to travel 10 light years? 10 light years is not, in the grand scheme of the universe, an especially large distance. We've talked, in previous conversations here at Late Space, about distances considerably larger. The width of our own galaxy, the reach of the observable universe itself. Numbers so large they eventually stop feeling like numbers at all and start feeling more like abstract ideas, floating somewhere beyond the ordinary reach of the human mind. 10 light years, by comparison, is almost modest. It would carry us only slightly beyond our very nearest stellar neighbours into a small, close cluster of stars that astronomers can list, comfortably by name. And yet, even this comparatively modest distance turns out to be genuinely, profoundly difficult to properly answer, because the honest answer depends entirely on what exactly you mean by us. Depends entirely on what technology we happen to be using. Depends on whether you're asking about the year 1977 or the year 2026 or some imagined future decade not yet arrived. The answer ranges, depending on these assumptions, from a genuinely startling number measured in hundreds of thousands of years, all the way down, in certain carefully imagined theoretical scenarios, to something considerably closer to a single human lifetime. Tonight, we're going to walk through all of it, slowly, patiently. Starting with the spacecraft we've actually built and launched, moving through the propulsion technologies currently being seriously developed and studied, and finally, gently, into the genuinely strange, genuinely beautiful territory of relativistic physics, where the very meaning of time itself begins to bend and stretch in ways that most people never properly get the chance to sit with. Close your eyes when you want to. We have all night for this. Let's begin, as we often do here, with something we can properly measure, properly hold, before we venture into anything more speculative or theoretical. 10 light years is a distance of approximately 94.6 trillion kilometers. Or, if you prefer the units more familiar in everyday American usage, about 58.8 trillion miles. Let's build this figure the way we build most figures here at Late Space. Patiently, step by step, from something smaller and more comprehensible. Light itself, moving at its fixed, unchanging speed of 299,792 kilometers per second is the fastest thing in the entire universe. Nothing with mass can ever match it, let alone exceed it. In a single second, light travels far enough to circle the entire Earth about 7.5 times. In a single minute, it covers roughly 18 million kilometers. In a single hour, roughly 1 billion kilometers. Already more than 6 times the entire distance separating Earth from the Sun. In a single day, light covers approximately 26 billion kilometers. And in a single year, patiently, relentlessly, without ever pausing or slowing, light travels a total distance of about 9.46 trillion kilometers. That is 1 light year, 9.46 trillion kilometers. 10 light years, then, simply multiplies this figure by 10. A distance of roughly 94.5 trillion kilometers, stretching outward from wherever you're currently resting into the quiet, mostly empty darkness of interstellar space. Within that specific radius, 10 light years from our own sun. Astronomers count a small, comfortably nameable handful of stellar neighbors. The Alpha Centauri system, which we explored together in a recent conversation, sits at 4.2 light years, the very nearest of all. Barnard's star sits a little further, at about 6 light years. Wolf 359, Lalande 21185, Sirius. That brilliant, familiar point of light, so often the brightest star in our own night sky. All sit somewhere within this same, comparatively close 10 light year sphere. It's a small, quiet neighborhood, astronomically speaking. Our own particular corner of a considerably larger galactic city. And the question we're asking tonight is genuinely, honestly this. Given everything we currently know, given everything we've actually built, and given everything we can seriously, credibly imagine building in the decades and centuries ahead, how long would it actually take to cross that particular 94.5 trillion kilometer gap? Let's start with what we've actually done. Not what's theoretically possible, not what future engineers might someday achieve, but what human beings, with the tools currently in our hands, have genuinely, physically accomplished. The fastest, most distant human-made object currently in existence is Voyager 1, a spacecraft we've discussed together in several previous conversations here at Late Space. Launched in September 1977, Voyager 1 has now been traveling continuously, faithfully, for nearly 50 years, and currently moves through interstellar space at a velocity of approximately 17 kilometers per second, roughly 61,000 kilometers per hour, or about 38,000 miles per hour. This is, by any ordinary, everyday human standard, an extraordinary speed. It would carry you from New York to Los Angeles in well under 2 minutes. It is considerably faster than any bullet, any commercial aircraft, any vehicle you have ever personally ridden inside. And yet, when measured against the specific, staggering scale of interstellar distance, this remarkable speed reveals itself to be genuinely, almost imperceptibly slow. Let's do the honest arithmetic together, patiently, the way we do all our arithmetic here at Late Space. At 17 kilometers per second, Voyager 1 would require approximately 176,000 years to cross a distance of 10 light years. I want to sit with that number properly, because it deserves considerably more than a passing mention. 176,000 years. This is a span of time roughly 6 times longer than the entire history of anatomically modern Homo sapiens. It stretches back, if you try to walk it in reverse from today, well before the earliest cave paintings, well before the earliest stone tools showing genuine symbolic complexity, into an era when our species was still small, scattered bands of hunter-gatherers, moving across landscapes that had not yet been mapped, named, or written about in any form that has survived to us today. At the speed of our fastest existing spacecraft, a machine that represents, genuinely, one of the great engineering triumphs of the 20th century. Crossing this comparatively modest 10 light-year distance would require a span of time considerably longer than the entire recorded history of human civilization. Wherever you are, I hope you're comfortable. Let's breathe here for a moment, letting that first foundational number settle properly before we start exploring the ways this timeline might genuinely, meaningfully be shortened. Because Voyager 1, remarkable as it is, was never actually designed for the specific task we're discussing tonight. It was built in the early 1970s using the propulsion technology and engineering knowledge available at that time, with a primary mission focused on flying past Jupiter and Saturn. A mission it accomplished brilliantly, gathering data and images that permanently transformed our understanding of the outer solar system. Its remarkable speed, sufficient for that original planetary mission, was never intended to represent humanity's best, most serious attempt at genuine interstellar travel. So let's ask a more properly focused question. Using the most advanced propulsion technologies currently available or currently being seriously developed and tested, how quickly could a purpose-built spacecraft, genuinely, specifically designed for the challenge of interstellar distance, actually travel? Let's start with chemical rockets, the same basic category of propulsion technology that has carried every crewed mission in human history, from the earliest Mercury and Gemini flights through the Apollo missions to the Moon, all the way to the modern rockets currently carrying astronauts and cargo to the International Space Station. Chemical rockets work by burning fuel, typically some combination of liquid hydrogen and liquid oxygen, or various other chemical propellant combinations, and expelling the resulting hot exhaust gas at high velocity out the back of the engine, generating forward thrust through simple, well-understood Newtonian physics. For every action, an equal and opposite reaction. The fundamental limitation of chemical rockets, for the specific purpose of interstellar travel, comes down to a piece of mathematics we've discussed together in earlier conversations here at Late Space. The rocket equation, first properly derived by the Russian scientist Konstantin Tsiolkovsky in 1903. This equation reveals something genuinely important, genuinely limiting, about chemical propulsion specifically. The amount of fuel required to achieve a given increase in velocity grows exponentially, not linearly, as your desired final speed increases. Doubling your desired velocity doesn't simply double your fuel requirement. It can easily quadruple it, or worse, depending on the specific exhaust velocity your particular engine and fuel combination achieves. For the specific, modest speeds required to reach Earth orbit, or even to travel to Mars or the outer planets, chemical rockets remain genuinely useful, genuinely practical. But for the dramatically higher speeds required to make any meaningful dent in a 10-light-year journey, chemical propulsion runs, quite quickly, into a wall that no amount of clever engineering can properly overcome. The fuel mass required simply grows too large, too fast, exceeding, by many orders of magnitude, anything that could plausibly be launched from Earth's surface or even assembled in orbit. This is where more advanced, more genuinely promising propulsion concepts enter our story. Technologies that either don't exist yet in fully operational form or exist only in early, limited, experimental stages, but that represent genuinely serious, genuinely credible areas of ongoing scientific and engineering research. Let's talk first about ion propulsion, a technology that, unlike some of what we'll discuss tonight, already exists, already flies, already represents a genuine, currently operational alternative to traditional chemical rockets. Ion engines work through a fundamentally different physical principle than chemical rockets. Rather than burning fuel and expelling hot exhaust gas, ion engines use electrical energy, typically generated by solar panels, or, in certain specialized designs, by nuclear power sources. To ionize a propellant, usually a noble gas like xenon, stripping electrons from individual atoms to create charged particles. These charged particles are then accelerated to extraordinarily high velocities using electric fields and expelled from the engine to generate thrust. The genuine advantage of ion propulsion lies in its remarkable fuel efficiency. While the actual thrust produced by an ion engine at any given moment is genuinely, comparatively weak, considerably weaker, in fact, than even a modest chemical rocket. Ion engines can sustain this gentle thrust continuously, patiently, for months or even years at a stretch, gradually, steadily building up considerably higher final velocities than chemical rockets, which burn through their entire fuel supply in a matter of minutes, could ever achieve. NASA's Deep Space One mission, launched in 1998, successfully demonstrated exactly this kind of ion propulsion technology, achieving an acceleration rate of approximately 25 kilometers per hour of additional speed, gained patiently each day through continuous, sustained ion thrust. If you scaled up this same basic technology considerably, imagining an ion engine roughly 10 times more powerful and efficient than Deep Space One's original demonstration system, careful calculations suggest you could theoretically accelerate a spacecraft to roughly half the speed of light, though doing so would require an extraordinarily long acceleration period on the order of several thousand years of continuous, patient thrust, simply to reach that theoretical maximum velocity. This reveals something genuinely important about ion propulsion's actual, practical usefulness for our specific 10 light-year question tonight. While genuinely more fuel-efficient than chemical rockets, and genuinely capable, given enough patient time, of reaching considerably higher final velocities, the specific acceleration rates achievable with currently demonstrated ion propulsion technology remain far too gradual, far too slow to properly build, to meaningfully shorten our overall journey time within any reasonable, human-relevant time frame. Let's talk, next, about nuclear propulsion, a considerably more powerful and considerably more theoretically promising category of technology, though one that remains, even now, largely in the research and early development stage, rather than genuine operational reality. Nuclear thermal propulsion works by using a nuclear reactor to superheat a propellant, typically liquid hydrogen, to extraordinarily high temperatures, then expelling this superheated gas through a rocket nozzle to generate thrust. A fundamentally similar basic mechanism to chemical rockets, but capable of achieving considerably higher exhaust velocities, because nuclear fission releases dramatically more energy, atom for atom, than any ordinary chemical reaction ever could. NASA has, in recent years, been actively developing and testing nuclear thermal propulsion technology specifically intended for future crewed missions to Mars, with demonstration missions currently planned for the coming decade. This technology, while genuinely useful, genuinely promising for meaningfully reducing travel times within our own solar system, potentially cutting Mars transit times roughly in half compared to current chemical propulsion, remains, even in its most optimistic projected forms, considerably too limited in its achievable final velocity to seriously address the specific, dramatically larger scale of interstellar distance we're discussing tonight. The considerably more theoretically powerful cousin of nuclear thermal propulsion is nuclear fusion propulsion, a technology that remains, even now, genuinely experimental, genuinely unproven in any practical, operational spacecraft context, but that represents, in the considered, careful judgment of many propulsion physicists and engineers, our most credible long-term path toward genuinely practical interstellar travel. Fusion propulsion would work by harnessing the same basic physical process that powers our own sun and every other star in the universe, forcing light atomic nuclei, typically hydrogen isotopes, to fuse together under extreme pressure and temperature, releasing tremendous quantities of energy in the process. If this energy could be properly, safely harnessed and directed for spacecraft propulsion, a genuinely significant engineering challenge that remains, even now, unsolved in any practical sense. The theoretical exhaust velocities achievable would be dramatically, meaningfully higher than anything chemical or even nuclear thermal propulsion could ever provide. Careful engineering projections suggest that a genuinely mature, fully developed fusion propulsion system, if such a thing were successfully built, might be capable of accelerating a spacecraft to somewhere between 10 and 15% of the speed of light, Wherever you are, I hope you're comfortable. Let's pause here properly, because this specific figure, somewhere between 10 and 15% of light speed, represents a genuinely important threshold in tonight's conversation and deserves careful, unhurried attention before we move any further. If a fusion-powered spacecraft could genuinely, reliably sustain a velocity of roughly 10% of the speed of light, approximately 30,000 kilometers per second, the mathematics of our 10 light-year journey begins to change considerably, and considerably more encouragingly than anything we've discussed so far tonight. At 10% of light speed, a journey of 10 light-years would require approximately 100 years. 100 years. Let's properly sit with the genuine significance of this figure, because it represents something categorically, meaningfully different from the 176,000-year timeline we calculated earlier for Voyager 1's current speed. 100 years remains, genuinely, considerably longer than any single human lifetime. It would still require, quite necessarily, either some form of multi-generational crewed mission, patiently passing the original journey's purpose and mission forward across several successive generations of travelers, or, more plausibly for any actual near-term mission, an entirely uncrewed robotic spacecraft launched by one generation of scientists and engineers, and eventually, patiently, faithfully received and studied by a considerably later generation, possibly including people not yet born at the moment of the original launch. But 100 years is also, genuinely, a time frame that connects, meaningfully, to actual human institutions, actual human memory, actual continuity of purpose and understanding. It's a span of time that grandparents can reasonably discuss with grandchildren. A span of time within which the specific scientific and cultural context of the original launch remains genuinely, meaningfully connected to whatever eventual result or discovery the mission ultimately produces. If fusion propulsion technology could genuinely, reliably be developed to this specific level of maturity, a considerable if representing decades, quite possibly a full century or more of continued dedicated scientific and engineering research still ahead of us, even now. A genuine, purpose-built mission to travel 10 light-years becomes something considerably more than pure fantasy. It becomes something closer to a genuinely serious, if still extraordinarily ambitious, long-term engineering goal. Let's talk now about the other genuinely serious category of proposed interstellar propulsion technology. One we've discussed together in an earlier conversation here at Late Space, in the specific context of Breakthrough Starshot and its recent, quiet struggles. Laser-driven light sail propulsion. The basic physical principle behind light sail propulsion is genuinely elegant, genuinely different in character from every other propulsion method we've discussed tonight. Rather than carrying fuel aboard the spacecraft itself and burning or otherwise expelling that fuel to generate thrust through a Newtonian reaction, light sail propulsion instead relies on radiation pressure. The small but genuine physical force that light itself exerts on any surface it strikes, a consequence of the fact that photons, while massless, still carry momentum. An extraordinarily thin, extraordinarily lightweight, highly reflective sail attached to a correspondingly tiny, minimally equipped spacecraft can be accelerated by shining an intense beam of light against it. Either sunlight itself for more modest, gradual acceleration, or, for considerably more dramatic results, an artificially generated, extraordinarily powerful laser beam projected from a ground-based or orbital laser array specifically built for this exact purpose. The specific advantage of this approach, for the particular challenge of interstellar travel, lies precisely in what it doesn't require. The spacecraft itself carries no propellant mass whatsoever, sidestepping entirely the exponential fuel mass problem embedded within Tsiolkovsky's rocket equation that so thoroughly limits chemical, and to a lesser but still meaningful extent, nuclear propulsion. Careful engineering projections for laser-driven light sail propulsion, using power levels genuinely, seriously discussed within current research literature. laser arrays generating somewhere in the range of 100 gigawatts of continuous, coordinated power, suggest that a sufficiently small, sufficiently lightweight spacecraft could theoretically be accelerated to approximately 20% of the speed of light within a relatively brief acceleration period lasting only a matter of minutes. At 20% of light speed, our 10-light-year journey would require approximately 50 years. 50 years is a genuinely, meaningfully shorter time frame than the 100-year figure we calculated for fusion propulsion just a few minutes ago, and considerably, dramatically shorter than Voyager 1's 176,000-year timeline. It represents a span of time comfortably within a single human career. Well, within the bounds of a single working lifetime for the scientists and engineers who might launch such a mission, meaning that, quite plausibly, some among the original mission team could reasonably expect to still be alive, still professionally active, when whatever data or images the mission eventually gathers finally, faithfully, makes its long, patient way back to Earth. But I want to be genuinely, carefully honest with you about the considerable engineering challenges still standing between this theoretical 50-year timeline and any actual operational mission. Challenges we explored together in more detail during our earlier conversation about Breakthrough Starshot's own quiet struggles. Building and precisely coordinating a laser array powerful enough to achieve this kind of acceleration represents an engineering challenge considerably beyond anything currently actually operational. The extraordinarily thin, extraordinarily lightweight sail material required must simultaneously be strong enough to survive the intense, concentrated force of the laser beam itself without tearing or melting, while remaining light enough that the modest available thrust can still achieve genuinely meaningful acceleration. And any spacecraft actually attempting this journey would need to survive, intact, a 50-year transit through the genuine hazards of interstellar space, including, as we discussed, the real, physically significant danger posed by even microscopic dust particles, which, at 20% of light speed, carry sufficient kinetic energy to seriously damage or entirely destroy a sufficiently fragile spacecraft on impact. These challenges remain genuinely unsolved, even now in 2026. Breakthrough Starshot's own specific effort to address them has, as we discussed in an earlier conversation, quietly stalled, its original ambitious timeline pushed indefinitely into an uncertain future. But the underlying physics, the basic principle that light itself can meaningfully accelerate a sufficiently lightweight spacecraft to a significant fraction of its own speed, remains genuinely, scientifically sound, representing, in the considered judgment of many propulsion researchers, one of our most credible, most physically achievable near to medium-term paths toward genuinely meaningful interstellar travel. Wherever you are, I hope you're still comfortable. Let's widen our view now, gently, and talk about what happens to our original question. How long would it take us to travel 10 light years? Once we move beyond currently demonstrated or seriously proposed near-term technology into the more genuinely theoretical, more genuinely speculative territory of what might, someday, in a considerably more distant future, become possible. I want to be careful, honest, and properly calibrated as we enter this next portion of tonight's conversation, distinguishing clearly, the way we always try to here at Late Space, between genuine, physically grounded speculation and pure, ungrounded fantasy. Let's talk, specifically, about what happens if we imagine a spacecraft capable of continuous acceleration. Not simply reaching some maximum velocity quickly and then coasting, the way each of the propulsion methods we've discussed so far would necessarily operate, but instead maintaining a steady, ongoing acceleration throughout the entire journey, continuously increasing its speed for as long as its engines and its fuel or energy supply allow. This specific scenario becomes genuinely interesting, genuinely worth exploring carefully because of a particular elegant coincidence in the underlying physics. If a spacecraft could sustain a constant acceleration of approximately 9.8 meters per second, the same rate of acceleration as Earth's own surface gravity, often written in physics notation simply as 1g. The people aboard that spacecraft would experience something remarkably similar to ordinary Earth gravity throughout their entire journey, without needing any kind of artificial rotating, structure, or other complicated engineering solution to simulate gravity. If such a spacecraft could accelerate continuously at this comfortable, Earth-like 1g rate for the first half of its journey, then flip around and decelerate at the same steady rate for the second half, gradually slowing back down as it approaches its ultimate destination, rather than simply crashing into it at tremendous velocity. The total travel time required to cross 10 light-years, calculated, properly using the full mathematics of special relativity, comes out to approximately 6 years, as experienced by the people actually aboard the spacecraft itself. I want to sit with that figure very carefully, very deliberately, because it represents one of the more genuinely strange, genuinely beautiful ideas in all of physics, and I don't want it to simply pass by without proper, unhurried attention. 6 years. A span of time considerably, dramatically shorter than any of the other figures we've discussed so far tonight. Shorter than the 50 years required by 20% light speed laser sail propulsion, shorter than the 100 years required by 10% light speed fusion propulsion, unimaginably shorter than the 176,000 years required by Voyager 1's actual current velocity. How is this possible? The answer lies in one of the genuinely central, genuinely mind-bending discoveries of Albert Einstein's special theory of relativity. The fact that time itself does not pass at the same, fixed, universal rate for every observer, but instead depends, in careful, precisely calculable ways, on an observer's own relative velocity. Here's how to properly understand this. As our imagined spacecraft continues its steady, constant 1g acceleration, it gradually approaches, ever more closely, the absolute speed limit of the universe itself, the speed of light. It can never actually reach this limit. Nothing with mass ever can, according to everything we currently understand about physics. But it can get remarkably, genuinely close, particularly during the later stages of its acceleration phase. And as any object's velocity approaches the speed of light, relativistic time dilation becomes increasingly, meaningfully significant. Time, as experienced by the people or instruments aboard that rapidly moving object, genuinely, measurably passes more slowly, relative to time as experienced by a stationary observer watching from outside. This is not a matter of mere perception or some kind of psychological trick of the mind. It is a genuine, physically real effect, confirmed repeatedly through countless careful experiments, and accounted for, quite practically, in the everyday operation of systems like GPS satellites, which experience measurably different rates of time passage than observers on Earth's surface, and must be precisely, continuously corrected for this genuine relativistic effect in order to maintain their remarkable navigational accuracy. For our imagined spacecraft, continuously accelerating at a comfortable 1g rate, this means that while the crew aboard would experience only approximately 6 years passing, according to their own onboard clocks and their own direct, personal experience of time, including, notably, their own aging process, which would proceed at this same, considerably slower relative rate. A considerably longer span of time would actually pass, meanwhile, back here on Earth. Let me walk through this properly, because I think the specific relationship between these two different measurements of elapsed time, what physicists call proper time, the time genuinely, personally experienced by the traveling observer, versus coordinate time, the time that passes for a stationary observer watching from a fixed reference point, deserves careful, patient attention. For our hypothetical 10 light-year, constant 1g acceleration journey, the 6 years of proper time experienced by the spacecraft's crew would correspond, back here on Earth, to a considerably longer span of elapsed coordinate time. A figure that careful relativistic calculations place somewhere in the range of 12 to 13 years, depending on the precise details of the acceleration and deceleration phases. I want to be genuinely careful here, because this specific example, a 10 light-year journey, actually represents a comparatively modest, comparatively gentle demonstration of relativistic time dilation, considerably less dramatic than what becomes possible over considerably longer relativistic journeys. Consider, for comparison, a similarly constant 1g acceleration journey to the Andromeda Galaxy, a genuinely enormous distance of approximately 2.5 million light-years, which we discussed together in an earlier conversation exploring the true scale of the observable universe. According to the same underlying relativistic mathematics, a crew aboard a spacecraft undergoing this kind of continuous, comfortable 1g acceleration and deceleration could, in principle, complete this genuinely staggering 2.5 million light-year round trip within approximately 58 years of their own personal, experienced proper time, even though, back here on Earth, considerably more than 5 million years would have actually genuinely elapsed during that same interval. This reveals something genuinely profound, genuinely worth sitting with carefully here at this particular hour in this particular quiet, given a sufficiently capable, sufficiently sustained propulsion system. One capable of maintaining continuous, comfortable acceleration for years at a stretch, a genuinely enormous engineering challenge that remains, even now, considerably beyond anything we currently know how to build. It becomes, in principle, physically possible to cross even the most staggering interstellar and intergalactic distances within a single human lifetime, as experienced, personally, by the traveller themselves. The cost of this remarkable capability, however, is genuinely, permanently significant. The traveller would return, if they returned at all, to a version of Earth that had aged considerably, meaningfully more than they themselves had. Friends, family, entire civilizations and cultural contexts would have moved forward through considerably more elapsed time than the traveller's own personal experience of the journey. Wherever you are, I hope you're comfortable. Let's spend some time now, gently, sitting with the genuine emotional and philosophical weight of what we've just discussed, because I think it deserves considerably more than a passing, purely technical mention. There is something genuinely, quietly strange, genuinely worth feeling properly in the idea that travelling far enough, fast enough, means genuinely, permanently stepping out of ordinary, shared human time. That the very act of reaching for these more distant destinations, even using propulsion technology we can only theoretically imagine, would necessarily mean leaving behind, forever, the particular moment in history, the particular version of Earth, the particular people and relationships that existed at the moment of departure. This is not, properly understood, a flaw or a failure in the physics. It is simply, honestly, what genuine interstellar travel, undertaken across genuinely vast distances at genuinely significant fractions of light speed, actually requires and actually costs. Time itself, properly understood, is not the fixed, universal backdrop against which all events simply uniformly unfold, the way it can sometimes feel in ordinary, everyday human experience. It is, instead, something considerably more fluid, considerably more genuinely tied to each individual observer's own particular path through the universe. I find something genuinely, quietly moving in this realization, properly sat with here, at this hour, in this particular quiet. The astronauts and engineers of some considerably distant future, undertaking genuinely serious interstellar missions using propulsion technology considerably beyond anything we currently possess, would face a choice and a cost considerably different from anything explorers throughout the whole of human history have previously encountered. Not simply the risk of danger or the hardship of a difficult, demanding journey, but the genuine, permanent separation from the specific flow of shared human time itself. A separation that would only grow more pronounced, more permanent, the faster and the further they chose to travel. Let's bring ourselves back now, gently, from this genuinely theoretical, genuinely speculative territory towards something a little more properly grounded in our current, actual technological reality. Because I think it's important, before we begin closing tonight's conversation, to properly hold both of these perspectives together. The genuine, sobering scale of our current limitations, alongside the genuine, careful promise of what future decades and centuries of continued research and development might, someday, make possible. Let's properly summarize, patiently, the range of answers we've built together tonight to our original, simple-sounding question: how long would it take us to travel 10 light years? Using Voyager 1's current, actual velocity, the fastest speed any human-made object has ever genuinely, physically achieved. The honest answer is approximately 176,000 years. Using ion propulsion technology, genuinely demonstrated, genuinely operational today, but scaled up considerably beyond its current, modest capabilities, the timeline could theoretically shrink to several thousand years, though achieving this would require an extraordinarily long, patient acceleration period, considerably beyond any currently planned or seriously proposed mission architecture. Using nuclear fusion propulsion, a technology that remains, even now, genuinely experimental, genuinely unproven in any operational spacecraft. But that represents a serious, credible area of ongoing scientific research. A hypothetical spacecraft capable of sustaining 10% of light speed could complete the journey in approximately 100 years, using laser-driven light sail propulsion of the specific kind seriously proposed by projects like Breakthrough Starshot. A technology that remains, as we discussed in an earlier conversation, genuinely stalled in its current, real-world development, but that rests on physically sound, scientifically credible underlying principles. A sufficiently small, sufficiently lightweight spacecraft, accelerated to approximately 20% of light speed, could theoretically complete the journey in approximately 50 years. And using a genuinely theoretical, continuously accelerating spacecraft, maintaining a comfortable, Earth-like 1G acceleration throughout its journey, a propulsion capability that remains, currently, considerably beyond anything we know how to actually build, requiring energy sources and engineering solutions well beyond our current technological horizon. The crew aboard such a vessel could, according to the genuine, carefully verified mathematics of special relativity, experience the entire 10 light-year journey in approximately 6 years of their own personal, lived time, even as considerably more time passed. Meanwhile, for everyone and everything they left behind on Earth, I want to spend some time now, gently, reflecting on what this entire range of possible answers actually reveals, properly understood, about the specific relationship between human ambition and the genuine physical scale of the universe we happen to find ourselves living within. There is something genuinely, quietly humbling, I think, in properly sitting with the fact that even our most optimistic, most carefully considered theoretical scenarios, technology that remains, even now, considerably beyond anything we currently know how to build, still require, at absolute minimum, several years, and more plausibly several decades, simply to cross a distance that represents, in the wider context of our own galaxy alone, an extraordinarily modest, extraordinarily local journey. Our entire galaxy spans roughly 100,000 light-years. 10 light-years, the specific distance we've spent this entire evening carefully exploring, represents only 1/10,000th of that considerably larger galactic diameter. And the fact that even this comparatively tiny fraction of our own galactic neighborhood remains, genuinely, so profoundly, so persistently difficult to actually physically cross, reveals something important, I think, about the true, honest scale of the challenge involved in any genuine, serious human ambition toward interstellar travel and exploration. And yet, and I want this "and yet" to carry real, genuine weight here, at this hour, in this particular quiet, there is something equally, genuinely remarkable, genuinely worth properly celebrating in the simple fact that we can even properly, carefully calculate these figures at all, that we possess, as a species, the mathematical and scientific understanding required to properly model exactly how a laser sail might accelerate a spacecraft, exactly how relativistic time dilation would genuinely affect a crew's personal experience of an otherwise impossibly long journey, exactly what specific engineering thresholds we would need to cross in specific, concrete, measurable terms in order to make each progressively faster propulsion scenario a genuine, practical reality. We do not yet possess the technology to actually make this specific 10 light-year journey within any reasonable, human-relevant time frame. But we possess, genuinely, remarkably, the understanding required to properly know exactly what we would need to build in order to eventually do so. A considerably different, considerably more hopeful position than simple, uninformed ignorance. Wherever you are, I hope you're still comfortable. Let's talk now, for a while, about the specific human story behind this ongoing, patient scientific effort, because I think the people actually doing this careful, painstaking research deserve genuine, proper attention here at the end of tonight's long conversation. The scientists and engineers currently working on nuclear fusion propulsion, laser sail technology, advanced ion drives, and the many other genuinely serious propulsion concepts we've touched on tonight are engaged, quite genuinely, in one of the more patient, more genuinely long-term intellectual projects our species has ever collectively undertaken. Many of them will not personally live to see their specific research fully, practically realized in any operational interstellar mission. Many of them are working, quite consciously, quite deliberately, on problems whose eventual solutions may not arrive for considerably longer than their own individual careers, or even their own individual lifetimes. And yet they continue this work anyway, carefully modeling laser array configurations, carefully testing new sail materials in laboratory conditions, carefully refining our theoretical understanding of fusion reactor physics, carefully building, piece by patient piece, the specific body of knowledge and capability that some considerably future generation of scientists and engineers will eventually, faithfully inherit and continue building further upon. This is, I think, one of the more genuinely beautiful, genuinely admirable qualities of properly conducted, patiently sustained scientific research, the willingness to invest real, meaningful effort into problems whose complete resolution may lie considerably beyond one's own personal, individual timeline. A willingness to trust, quite genuinely, that careful, patient, honest work, properly documented and properly passed forward, retains real value and real significance, even if, especially if, its ultimate fruition arrives only for those who come considerably after. You, tonight, having spent this entire evening properly, carefully working through the genuine physics and genuine engineering challenges involved in this specific question, are, in your own small, quiet way, participating in this same broader tradition. The patient, careful human effort to properly understand exactly what stands between us and the stars, and exactly what it would genuinely require to eventually, someday, cross that distance. I want to offer you one more perspective now, before we begin properly closing tonight's conversation, because I think it connects everything we've discussed this evening into something genuinely worth carrying with you towards sleep. 10 light years, properly, honestly understood, sits at a genuinely interesting, genuinely instructive threshold within the wider context of everything we've explored together across our many conversations here at Late Space. It's close enough that we can, at least in careful theoretical terms, credibly imagine crossing it within a single human lifetime, given sufficiently advanced propulsion technology. And yet it remains, even now, using every currently available or currently seriously proposed technology, genuinely, meaningfully beyond our actual practical reach. This particular, specific tension, genuinely imaginable, yet genuinely unreachable, at least for now, feels, to me, like an honest, properly calibrated reflection of where our species actually genuinely stands right now, in this particular moment, in our own long, patient relationship with the wider universe surrounding us. We are not the civilization that will complete this specific journey, not within any of our own individual lifetimes, and, quite probably, not within several generations still to come. But we are, genuinely, meaningfully, the civilization that is properly, carefully, patiently laying the specific scientific and engineering groundwork that will eventually, someday, make this journey genuinely possible. Testing sail materials, refining fusion reactor designs, carefully mapping out exactly what propulsion thresholds must eventually be crossed, and exactly what genuine physical and engineering challenges must eventually, patiently be solved. That is not, I think, a small or a disappointing thing to properly sit with, here, at this hour, in this particular quiet. It is, instead, a genuinely meaningful, genuinely significant form of contribution. The patient, careful, honest work of properly understanding a problem thoroughly enough that some considerably future generation, inheriting our accumulated knowledge and our accumulated understanding, might eventually, faithfully, finally solve it. Let's come down now, slowly, gently, toward the end of tonight's long conversation. Here is what is true, as carefully and as honestly as I can leave it with you. 10 light years is a distance of approximately 94.5 trillion kilometers. Using our fastest currently existing spacecraft, Voyager 1, crossing this distance would require approximately 176,000 years. Using nuclear fusion propulsion technology that remains, even now, genuinely experimental but scientifically credible, a spacecraft capable of sustaining 10% of light speed could complete this same journey in approximately 100 years. Using laser-driven light sail propulsion, of the kind seriously proposed by projects like Breakthrough Starshot, a sufficiently lightweight spacecraft accelerated to 20% of light speed could complete the journey in approximately 50 years. And using a genuinely theoretical spacecraft, capable of sustaining continuous, comfortable, Earth-like acceleration throughout its entire journey, the crew aboard could, according to the properly verified mathematics of special relativity, experience this same 10 light-year journey in approximately 6 years of their own personal, lived time. None of these more optimistic, more theoretically advanced propulsion scenarios currently exist in any genuinely operational form. All of them represent genuine, serious, ongoing areas of scientific and engineering research. Patient, careful, long-term work being conducted right now by real scientists and engineers working toward a specific, concrete, eventually achievable goal, even if that goal's complete fulfillment remains, for now, considerably beyond our current technological reach. This is not, properly understood, a discouraging place to arrive at, here, at the end of tonight's long conversation. It is, instead, an honest, properly calibrated reflection of exactly where our species genuinely stands, right now, in our own long, patient relationship with the wider universe. Capable of properly, carefully calculating exactly what would be required to eventually cross even the vast distances separating us from our nearest stellar neighbors, even as we continue, patiently, faithfully, the genuine, ongoing work of actually building the specific technology required to eventually, someday, make that journey real. I want to leave you with one final image before we close, because I think it captures, better than any additional number or calculation could, the particular feeling I hope you carry with you into sleep tonight. Picture, if you can, the specific span of 10 light years stretching outward from wherever you're currently resting. Not as an abstract number, not as 94 trillion kilometers written out in careful scientific notation, but as an actual, physical, traversable distance filled with the small handful of nearby stars we mentioned earlier tonight. Alpha Centauri, Barnard's star, Sirius, and several others besides, each one sitting patiently in its own particular direction, its own particular corner of our shared, comparatively modest galactic neighborhood. And picture, too, the specific, patient chain of human effort required to eventually, someday, properly cross that distance. The careful laboratory work currently being conducted on fusion reactor containment, the careful materials science research currently refining ever thinner, ever more reflective sail fabrics, the careful, patient mathematics of relativistic physics worked out slowly, carefully, across more than a century of dedicated theoretical research, beginning with Einstein himself and continuing, faithfully, through generations of physicists who came after him. None of this work is complete. None of it will likely be complete within your own individual lifetime, or even within several generations still to come. But all of it, properly, patiently continues. Careful, honest, dedicated human effort, slowly, faithfully building toward a goal that remains, for now, genuinely beyond our reach. But that grows, patiently, incrementally, a little more genuinely possible with each careful year of continued research and development. Close your eyes, if they're not already closed. Somewhere out there, roughly 10 light years from where you're resting right now, a small handful of quiet, patient stars continue their own long, slow orbits, entirely unaware of, entirely indifferent to, the careful human effort currently, patiently working toward the day when something built by our hands might eventually, genuinely reach them. That day is not today. It may not arrive for considerably longer than any of our own individual lifetimes. But the careful, patient work continues anyway. In laboratories, in universities, in careful theoretical calculations worked out patiently on chalkboards and computer screens, slowly, faithfully building toward a future in which the specific question we've spent this entire evening properly exploring together might, someday, finally receive a considerably shorter, considerably more hopeful answer. Thank you for spending tonight here. Thank you for sitting patiently with numbers this large, this genuinely challenging, and letting them settle properly, honestly, without needing them resolved before you could rest. Sleep well, and somewhere, 10 light years away, in the quiet dark between here and there, the patient work of eventually, someday, crossing that distance continues. Slowly, carefully, faithfully, one careful calculation, one careful experiment, one patient generation at a time. Good night.